This is going to be a continuation of our video on dot structures. And here we're going to talk about exceptions to the octet rule. So there are two types of exceptions to the octet rule. The first are the electron deficient structures, which is kind of what it sounds like. The central atom has less than 8 electrons. In other words, we don't have enough electrons to satisfy the octet rule. Your classic example are the beryllium and boron compounds. Now, if you look at boron, boron is only going to have 3 valence electrons. So if we're going to think of a bond as a shared pair, and one electron comes from the boron, and one electron comes from what the boron is binding to, then boron can only form 3 bonds. So you can never have more than 3 electron pairs around the boron, hence the term electron deficient. Your second category are the expanded valence shells, which is again what it sounds like, where the central atom has more than 8 valence electrons. Now for your expanded valence shells, your element has to be, your central atom has to be from a period 3 or higher. So, for example, sulfur, phosphorus, chlorine, and bromine. Not to say that these elements don't form compounds that do follow the octet rule. They do. But they also form many compounds that do not follow the octet rule. Some examples: SF4, PF5, SF6, XEF2, XEF4. All these violate the octet rule and have more than 4 electron pairs around the central atom. Now some of these you ought to be able to look at the formula and tell that it violates the octet rule. Okay, SF4, not so much. You would have to draw out the structure for SF4. But what about PF5? That's clearly going to violate the octet rule because you have 5 attached atoms to the phosphorus. That means you're going to have 5 electron pairs around the phosphorus. Same thing here, SF6, you're going to have 6 electron pairs around the sulfur. And why would these two violate the octet rule? Because xenon has 8 electrons to start out with. Okay, xenon really doesn't like to form compounds to begin with. It can only do it under extreme conditions. But because xenon has 8 valence electrons to start out with, any xenon compounds will have more than 8 electrons, or will have more than 4 pairs around the central atom. So what about that formula that I gave you in the previous video where you figure out the number of bonds in a molecule? What would happen if we tried to apply that formula to a compound that does not follow the octet rule? So what about sulfur tetrafluoride? What if you didn't recognize this as a compound with an expanded valence shell, and we tried to use that formula to figure out the number of bonds? So we'd say sulfur has 6 valence electrons, and we got 4 fluorines, each of which has 7 valence electrons. 4 times 7 is 28. 28 and 6 is 34. Okay. And then we have 5 atoms total, right? And 5 times 8 is 40. Okay, so this is what we have, and this is what we want. So we take the difference between the two and divide it by 2. So 40 minus 34 over 2 is 6 over 2, which comes out to be 3 bonds. And now you see we have a problem. We would have to have a minimum of 4 bonds. How can we bind 4 fluorine atoms to the sulfur with only 3 bonds? You can't do it. It doesn't work. So you can't apply that formula to something that doesn't follow the octet rule. Now that formula is useful because it will let you figure out the number of bonds for compounds that follow the octet rule. For other compounds, we need an alternate procedure. So, first thing we're going to do, some of this is going to look familiar. First thing we're going to do is determine the number of electrons available to the molecule. That's the same as in the previous procedure. Then we're going to draw a skeletal structure that has only single bonds. Then we will add unshared electron pairs to the attached atoms to give each an octet. We will add any remaining electron pairs to the central atom. Okay. If the central atom does not have an octet at this point, we'll change one or more single bonds to double bonds. And if necessary, we'll change one or more single bonds to double bonds in order to obtain more desirable formal charges. So let's work through an example. Let's do SOCl2. We'll work through this whole procedure. Alright, so first step, determine the number of electrons available to the molecule. So we have a sulfur, we have an oxygen, and we have 2 chlorines. 2 chlorines, that's 14 electrons. Oxygen and sulfur are in the same group and have the same number of valence electrons, which is 6. 12 and 14 give us 26 electrons. Okay? So then we'll draw a skeletal structure that contains only single bonds. Sulfur is the central atom, so the sulfur will bind to the 2 chlorines and the oxygen. That gives us this structure. Okay. Then we'll add unshared electron pairs to the attached atoms to give each an octet. Right, so we have only single bonds. At this point, every atom is bonded by a single bond, so we're going to need to add 3 electron pairs, 3 unshared pairs to each of the attached atoms. Okay, that gives us this structure. So we're not quite done yet because we figured we had 26 electrons. We used 24. So we got 2 electrons left, and we don't have, and you look at this and say we don't have an octet on the sulfur either. So that's the next procedure, if we have any electrons left over to the central atom. So we had 24. We had 26, we used 24, that's 2 left over, so we put them on the sulfur. Okay, so now it would appear that everybody's happy. It would appear that everybody's happy. We have 8 electrons here, we have 8 electrons here, we have 8 electrons here, and we have 8 electrons here. Everybody's happy. Everybody has 8 valence electrons. Let's see, do we have the right number of electrons? 2, 4, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We have the right number of electrons. Every atom has an octet of electrons, and if you work out the formal charges, it's positive on the sulfur, negative on the chlorine. So this seems like an okay structure. It is probably not the best one that we can draw. Okay? So the next part of this procedure says if the central atom does not have an octet, change one or more single bonds to double bonds. That doesn't apply here. Our sulfur had an octet. And our last step is, if necessary, change one or more single bonds to double bonds to obtain more desirable formal charges. So what happens if we go in here and let's say, what happens if we go in and we say, let's move one of these unshared pairs. Let's move one of these unshared pairs to here. And let's change this single bond into a double bond. Okay, all we're doing is going here to here is changing an unshared pair and moving it here, and it becomes a bonding pair. Okay, so we're basically sharing more electrons, and that gives this structure. Well, let's look at this. 1, 2, 3, 4, 5, 6, and 6 minus 6 is 0, so we got rid of this formal charge. We got rid of the formal charge, and in fact we got rid of this formal charge as well. Right, so 1, 2, 3, 4, 5, 6, 6 minus 6 is 0. This structure has no formal charges. And if you remember some of our rules for deciding formal charges, one of them was it's always preferable to have the lowest number of formal charges. So here we got rid of the formal charges entirely. Now note that this second structure violates the octet rule for sulfur. Look at what we got here. Look at how many electron pairs we have. 1, 2, 3, 4, 5. We got 5 electron pairs around the sulfur. That violates the octet rule. That would not be okay for oxygen, but it's okay for sulfur. You can have more than 4 electron pairs around sulfur. So the second structure violates the octet rule for sulfur, but this is okay for sulfur. And it's the better structure because it reduces the number of formal charges. Okay. Now you might want to ask the question, could we have done the same thing with the chlorine? What if instead of moving an electron pair from the oxygen, what if we'd have changed one of these bonds into the double bond? Could we have done that? And the answer is yes, that you could have, but the structure wouldn't be as good because that would put charges on the chlorine, and you'd still have the negative charge on the oxygen. So you would still have a structure with two. You'd still have a structure. You'd have a positive charge. Basically, the net effect is we'd move the positive charge from the sulfur to the chlorine. All right. So let's look at one more example. Okay, let's do another example. Let's talk about perchlorate ion, ClO4-. Let's follow this procedure all the way through for perchlorate. So the first thing we'll want to do is determine the number of bonds or number of electrons available to the molecule. So chlorine has 7 valence electrons. We have 4 oxygens. 4 times 6 is 24. You add that up and it's 31. But then I added 1 electron to the count because it's a polyatomic ion. It's ClO4-. So we come out to have 32 electrons. Okay? So our second part of our procedure is that we draw a skeletal structure that contains only single bonds. We draw a skeletal structure that has only single bonds. Right? So chlorine's the central atom. We have our 4 attached oxygens. So then we add unshared electron pairs to the attached atoms to give each an octet, right? So each is a single bond, singly bonded atom, so we're going to add 3 pairs to each one. Okay, so 3 unshared pairs to each of the oxygen. We don't add anything to the chlorine. And I've already figured out the formal charges here, that each oxygen has a -1 formal charge, and the chlorine has a +3 negative charge. Okay. So then we add any remaining electrons to the central atom. We don't have to worry about this step. We've already used all our electrons. We figured out that we had 32 electrons. We've already used 32. And besides that, the central atom has an octet of electrons already. So we don't have to worry about adding any, and we don't have to worry about step 5 then. And if the central atom does not have an octet, change one or more single bonds to double bonds, we don't have to worry about that because it already has an octet. Okay. So it would seem like this would seem like an okay structure. Everybody has every atom has an octet of electrons, except for this. Well, except for two things. We've put up a fairly large positive charge on an electronegative element. Now, chlorine is not as electronegative as nitrogen, oxygen, or fluorine, but it's still an electronegative element. And also, we have a positive charge, or not a positive charge, but we have a formal charge on every single atom in the structure, which is not really good. So let's look at our last rule here then. That if necessary, we change one or more single bonds to double bonds to obtain more desirable formal charges. So the first structure is the same as what I had on the previous page with all single bonds. So what happens what happens if we convert one of these single bonds into a double bond? So we're going to take one of these unshared pairs and move it here so that unshared pair becomes a bonding pair. Okay, and look at what happens. First of all, two things happen. First of all, this formal charge goes away, because singly bonded oxygen is always -1, doubly bonded oxygen is always 0. This formal charge goes away, and the charge on the chlorine comes down from +3 to +2. So that's good for formal charges. So we got rid of one formal charge, and we brought the charge on the chlorine down by 1. Now, this structure violates the octet rule. We have 1, 2, 3, 4, 5 electron pairs around the central atom, but that's okay for chlorine. So could we carry this one step further? Okay, so we could do one more structure. What if we wanted to do one more structure? So now let's do the same thing again. Let's convert a unshared pair into a bonding pair. And so now we're going to get rid of a second formal charge. Okay, so this formal charge disappears. It becomes 0. And we bring the charge on the chlorine down from +2, now it's down to +1. And you can probably see where we're going with this now. If we do it one more time, let's say we convert this unshared pair into a bonding pair. Okay, and this formal charge goes away. So not only does this formal charge go away, but this one goes away as well, because we've now brought the charge on the chlorine down to 0. So in this structure, we've got rid of all the formal charges except for the one on the singly bonded oxygen. Now you might want to ask, okay, could we carry this one step further? What if we did the same thing and we converted an unshared pair here and into another bonding pair? What would happen? Well, this formal charge would go away. This would become 0. But we would now swing in the other direction. We'd have a negative charge on the central atom, on the chlorine. So we would not be accomplishing that much. We can't get rid of the formal charges entirely. Okay. So if we did do that, the negative charge would be on the chlorine instead of the oxygen, which wouldn't be a bad structure, but it's probably better to have the negative charge on the oxygen because the oxygen is the more electronegative element. Now this shows a point that I think is kind of important, that the formal charge of a central atom becomes 0 when the number of bonds equals the number of valence electrons. Okay? Because of the way we count formal charge by splitting the electrons up equally. So when chlorine has 7 bonds, like we have here, and then the formal charge becomes 0. This is the same reason, for example, why you will see sulfur drawn like this, or sulfate rather. You will often see the structure for sulfate ion drawn like this. Because sulfur has 6 valence electrons. So this is the structure that reduces the formal charge on the sulfur to 0. This is just one of several structures, but this is the one that gives the sulfur a 0 formal charge. And it's also the same reason, for example, with phosphorus. Phosphorus has 5 valence electrons. So the structure for phosphate is often drawn with 1 double bond and 3 single bonds, because that's the structure that gives phosphorus a 0 formal charge. So this formula overall, this formula isn't quite as clear-cut as the first one that I taught you, because here it's you kind of have to play around with it a little bit, move some things around and see what you can do to reduce the formal charges and get the best structure that you can. And that wraps up this video.